Okay, now we're going to start figuring out how to actually calculate radiometric dates. This is question 11, which we temporarily skipped. And here, what I'm asking you to do is calculate the age of a sample based on the amount of the original isotope. Based on means you know that already. Based on the amount of isotope remaining, and based on how long each half-life is. As an example, suppose you had carbon-14. The half-life of carbon-14 is 5,730 years, and you would need to know that. Notice that after every half-life, we go from 1 to a half, to a quarter, to an eighth, to a 16th, to a 32nd, to a 64th, and so on. And each time a half-life occurs, that's another 5,730 years. Okay? So after every half-life, and remember the length of the half-life is constant for any particular isotope. Okay, so suppose we had, just for sake of argument, 1/8. Okay? How many half-lives have gone by? Well, you might say, oh, 3 instantly. But how do you know that? Suppose instead of that, I said 1/64th as much as you started with. Well, you might say, okay, if I start with 1, after one half-life, I'm going to divide that by 2 and I'm going to get a half. After another half-life, I'm going to have a quarter. After another half-life, I'm going to have an eighth. After another half-life, I'm going to have a 16th. After another half-life, I'm going to have a 32nd. After another half-life, I'm going to have a 64th. Which means that I had to divide by 2 once, twice, 3 times, 4 times, 5 times, 6 times. So there have been 6 half-lives that have gone by. So what you do is you have to figure out how many half-lives you had passed by based on what you have now and what you started with, which is what we said over here. Okay? And so how would you put that? Well, I'm going to cheat here and just print this out immediately. You're going to divide the original isotope by 2 until you get the amount of isotope remaining. The number of half-lives, or the number of times you divide it by 2 is equal to the number of half-lives that have passed by or elapsed. And since every radioactive isotope has a unique half-life, you're then going to multiply the number of half-lives by the duration of the half-life. A lot of students took the half-life and divided it by 2. Remember that it's not, the half-life isn't what gets divided by 2. It's the amount of isotope that gets divided by 2, not the half-life. So the number of half-lives goes up by 1 half-life each time you have a half-life go by. Okay? And that brings us to our first actual applied question. And that one, we have to scroll down to, I think it's 15, yes. Here's question 15. This one, people freak out because there are lots of numbers here. But the numbers are pretty simple. Okay, the first thing we have is the half-life of carbon-14 is 5,730 years. So that's how long it takes for carbon-14 to be cut in half. Every time 5,730 years goes by, the amount of carbon-14 in a sample goes away by half. It's divided by 2. Now, the interesting thing about carbon-14, and very different from most isotopes, is the amount of carbon-14 in our atmosphere is pretty constant. The reason that it's pretty constant is that it's formed when cosmic rays from outer space bombard the upper atmosphere. What actually happens is they hit nitrogen-14 and turn it into carbon-14. And that means that we're always forming carbon-14 in the upper atmosphere. Excuse me. that means that over time, the amount of carbon-14 in the atmosphere stays pretty constant. And that means that if we measure the amount of carbon-14 in the atmosphere, that is the same as the amount of carbon-14 in any sample when it started. Okay, so that's the original amount. Now, as it says here, the amount of carbon-14 in terms of total carbon is tiny. It's very difficult to actually measure carbon-14. But because carbon-14 is radioactive, we can detect the decay of carbon. And because the rate of decay decreases as the amount decreases, instead of using the amount, we can simply measure the decay rate. And so, if, for instance, today it decayed at 1,000 decays per minute, after one half-life it would be decaying at 500 dpm, after 2, 250 dpm, after 3, 125 dpm, after 4, 62.5, and so on and so on and so on. And that means that if we find an old piece of carbon, say a piece of charcoal from a fire that cavemen were using thousands of years ago, and we measure the decay rate, and it's 500 dpm, and we know that it originally decayed at 1,000 dpm, we know that one half-life has gone by, and we can use that as a way of dating it. One half-life times 5,730 is 5,730 years, and we would know it would be that old. So, let's imagine that today we have a sample of wood that, because of the carbon-14 in it, is decaying at 65,536. Now, there's actually a reason for that number, but 65,536 decays per minute. Well, that means that's how much the normal rate of decay of new carbon is. If we have a piece of charcoal from an old fireplace that is undergoing 8,192 decays per minute, how old is the charcoal? Well, in order to figure that out, we start with 65,500, I've lost it, and 36 decays per minute. How fast is that going to decay after one half-life? Divided by 2. Okay, that's 3, that's 2, that's 7, that's 6, that's 8. After one half-life, it's going to be decaying at 32,768 decays per minute. How fast will it be decaying after another half-life? Let's divide that by 2. So that's 1, that's 6, that's 3, that's 8, and that's 4. After 2 half-lives, it's been divided by 2 twice, so that's 2 half-lives. It's decaying at 16,384 decays per minute. After another half-life, and by the way, you're welcome to use a calculator for this. You don't have to divide it along here. And I will include calculators on the next exam as well. You can, there will be a calculator available to you on screen through Honor Roll. Okay, 16,384 divided by 2. That's 8, that's 1, that's 9, that's 2. 8,192 decays per minute. That looks familiar. Okay? How many half-lives have gone by in that amount of time? Well, we've divided by 2 3 times, so we have had 3 half-lives go by. So how old is the sample? Well, you could say it's 3 half-lives, but I want to know how old it is in years. And since we know, excuse me, that the half-life of carbon-14 is 5,730 years, 5,730 years times 3, that's 15, that's 17,190 years. And that's how old the sample is. Okay? Now that's a lot of numbers, but the math is not hard, really. You're dividing by 2 and multiplying by 3. I think you all have the ability to do that. And certainly with a calculator you can do that. Okay? So let's go to the answer. And it says, show all your work. Okay? What would you do? You would say 65,536 divided by 2 equals, oh, I shouldn't have erased those, 32,000, oh shoot, something. Okay, I'm going to round it since I idiotically erased those numbers. 32,000, I'm just going to say 32,000. Okay? Then, 32,000 divided by 2 equals 16,000, and I think we can do that pretty easily. And then 16,000 divided by 2 equals 8,000. Oops. And of course, you would substitute the actual numbers for those zeros, because like I said, I was an idiot. Well, that one actually we know is 192. Okay? And so that means 3 half-lives. And you can just write that down, because you've shown how to do it right here. That's what I would expect you to do. And then you would say 3 times 5,730 years equals 17,000, and I don't even remember what it was, 190, I think, years. Okay, and that would be your complete answer. Again, not complex math. Okay. Now here, radiometric dating calculations. Here's another one. The half-life of potassium-40 is approximately 1.3 billion years. And we saw, in the case of the beta decay, that it turns into argon-40. And that gets trapped. Argon is a gas, but it gets trapped inside igneous rocks as the potassium-40 decays. If you heat up that rock, you can actually get it to be released. But we're going to assume here that we have a rock that cooled off once and didn't get heated up again. If we find a sample of granite in which the ratio of argon-40 to potassium-40 is 3 to 1, remember, that's the parent, or excuse me, that's the daughter, and this is the parent. So the daughter to parent ratio is 3 to 1. Well, what does that tell us? That tells us that the parent is 1 over 3 plus 1, or 1/4. And since we know that 1 divided by 2 equals 1/2, and then 1/2 divided by 2 equals 1/4, 2 half-lives have gone by. Since the half-life is 1.3 billion years, that means you could even write it like this: 2 half-lives times, 2 half-lives times 1.3 billion years per half-life. If you wanted to include it that way, you can see that the HL cancels, and that equals 2.6 billion years. Okay? And that's the answer to that question. Okay, now the next two questions deal with caveats. Caveats are warnings that you have to be aware of, things that have to be true in order to do radiometric dating. And if you look for the word caveat in the Geologic Time webpage, you'll see it's way down here near the bottom. And there are 3 caveats that have to be true in order for you to successfully do radioactive dating. 1, you must have a closed system. What that means is that if weathering or metamorphism has allowed ions to migrate or gases to migrate into or out of the rock that you're trying to date, then you can't successfully date it. At least you have a lot more difficult time. And since metamorphism obviously affects metamorphic rocks, weathering affects sediments and therefore sedimentary rocks, the best type of rock to use, generally speaking, are fresh pieces of igneous rock, igneous rocks that haven't been metamorphosed and haven't been weathered. The second thing, remember that graph that showed how much of the parent isotope there was? It decreases over time. Eventually, there's a practical limit. Eventually, you get to a point where you simply can't measure the amount of parent isotope because it's too small. That limit is generally around 10 half-lives. So if 10 half-lives have elapsed, then there's too little of the parent isotope to measure. Any measurements you have will be errors in the device you're using. They will be contamination. They will be cosmic rays coming from space. They will be things that do not allow you to get an accurate and precise measurement. So you have to use an isotope that has had less than 10 half-lives elapse for you to successfully measure the amount. Okay? Our third thing, you must be dating the correct event. What does that mean? Well, here's an example. Suppose you find a granite pebble in a conglomerate. A conglomerate, remember, is a sedimentary rock with pebbles and boulders and cobbles and gravel. Granite is igneous, and so it's often a really good rock to measure the radiometric date. But what are you measuring with that? You're not measuring when that granite was broken out of a mountainside, rolled down a river, became a pebble, and then got lodged into what eventually became a conglomerate. What you're measuring is when that granite cooled off. So don't think that you might say, oh, this granite is 1 billion years ago, therefore that conglomerate is 1 billion years old. No, that conglomerate is younger because it formed long after the granite formed. So all that does is it gives you a maximum age. It doesn't tell you when the thing that it was made out of formed. And so as another example, suppose you have a chunk of limestone from the Ocala Formation. This is the common limestone in north central Florida. It's about 40 feet under my feet right now in Gainesville. If you make a tabletop out of a piece of Ocala limestone, which people do, it's got lots of fossils, it's real pretty. You're not going to say that tabletop is 35 to 50 million years old. You're going to say the rock that it's made from is 35 to 50 million years, and that's a different thing. Okay? So, as an example, we have here a researcher analyzes a piece of coal from the age of the dinosaurs. We know dinosaurs lived from about 250 to about 65 million years old. So I'm saying roughly 100 million years. Okay? Suppose a researcher takes that and measures the decay rate of carbon-14 and gets 1 decay per minute. Remember that we said for that earlier problem that carbon-14 decayed at, we're assuming, 65,536 decays per minute. Well, if you divide 65,536 by 2 16 times, you'll get 1, which implies that this piece of coal dates from a period of time 16 carbon-14 half-lives ago. And if you take 16 and multiply it by the half-life of carbon-14, which is 5,736 years, you're going to get 91,680 years. And you're going to say, wait, that's way less than 100 million years. And so you might say, well, that means that the geologic time scale is all messed up and that there were dinosaurs 91,000 years ago. Obviously, the problem is that after 16 half-lives, you cannot get an accurate measurement of the amount of carbon-14 in coal after, look at this, 100 million years. Take 100 million, try this. Take 100 million years divided by 5,730 years, and you're going to find out that it's going to be something like 100,000 half-lives. How much carbon-14 is left after 100,000 half-lives? None. Okay? And that one carbon-14 decay that was measured per minute is not a real measurement. So the problem is that, not that the researcher made a math error, but that too many half-lives have gone by and not enough carbon-14 is left in order to make an accurate measurement. So this is, you could say, I don't actually have the number, but I mean as formally, but you could say this is caveat number 2, that that's the case. And the reason is that too little of the isotope is left to make that measurement. Okay. Our last question before our relative time exercise. A researcher analyzes an obsidian, which is volcanic glass, arrowhead, and finds that the ratio of argon-40 to potassium-40 is 1:1. That implies, if you remember back to our daughter-to-parent ratio questions, that implies that one half-life has gone by, and since the half-life of potassium-40 is 1.3 billion years, that implies that according to this researcher, that the arrowhead is 1.3 billion years. What is 1.3 billion years old? Not the arrowhead, but the rock that it's made from. And believe it or not, this error has been made. People have occasionally analyzed old artifacts and they've measured the radiometric age and said that's how old the artifact is, when it's not the artifact, it's the rock that it's made from. Okay? Hope you all understand how to do this. I'm going to stop now and we will look at the relative time exercise, the relative time question next.